All right. Hello, Dr. Gurel. This is Sheldon Larson, Samuel Clayton, and Zach Robinson checking in for our Lab 4 presentation where we looked at rotary lift and drag in biomechanics, specifically in a maple seedling as it fell. And we learned a lot, and so we'll go ahead and present a little bit about some of the principles and things that we gained from this lab.
So as we began studying drag and lift in class, we began looking for objects outside of class, just looking around us to find examples of what we were experiencing. And we found this in the sycamore maple tree. So what we decided to do was our goal here with this lab was to better understand how the shape and weight would let us recreate the falling behavior that this seed effect that we'd see here.
So as we looked into this comparison, we drew parallels to helicopter blades, and we were actually able to find some technical sources on helicopter blades and the principles there. And we found that the main two principles in play were drag and lift. Obviously, both of those going to counteract gravity. And so the way this works is, in both cases, both for the seedling and for the helicopter, gravity obviously acts in the downward direction. Drag acts on the body upward, but then because you have this rotating fin or airfoil type shape, you actually also get lift that is counteracting gravity. And it's important to remember that lift acts perpendicular to flow, but because, as you can see here in this slow motion video, because it spins around and that airfoil is nearly perpendicular or nearly parallel to the ground, the slicing through the air creates lift in the perpendicular and thus upward direction.
So kind of part of our lab as well, we wanted to demonstrate or recreate this with a model. So we built a model out of simple supplies like paper and a paper clip, and we were able to reproduce these results. So here you can see our scaled model. It's about a 1:4 in length and width scaled model from our prototype. So as can be seen here, our seedling as it falls, and we were able to compare that with how our model fell and reproduce those results. So here is a video of the seedling as it falls. Oh, excuse me. Sorry, that's... So here's the seedling as it falls. As can be clearly seen there, that motion that Sam described. And then in the next video, you will see our model as it falls, and it again mimics that same motion and rate of descent. So we were able to model that, and if we were to do future research on this or wanted to understand it more, we would look at the effect of the vein structure. Obviously, having a more dense leading edge here helps produce that angle of attack as well as determine the airfoil. We'd also play around with the geometric constraints of it. Why is this seedling produced in this form? How would changing those parameters give a different result? And so some applications of this, obviously there's already toys that mimic the same free fall of the maple seedling, and so understanding that and applications in that, as well as parachutes or trying to slow free fall, how this would fit into maybe even military applications. And again, this has been looked back as far as Da Vinci. This was his design for slowing down a person in free fall. So looking into those applications, there's really a lot of directions you could go with this. And so we were excited to look at these sources, really understand kind of rotary free fall and how lift and drag play a role in that, and overall gained a lot from this lab. So we appreciate the opportunity to do this and hope you have a Merry Christmas.